invitation. I'm going to talk about darkness beyond. I'm going to talk about darkness beyond unitarity. It will be clear in a second what I mean by that. This is a unifying theme for two different thread of works. One of them completed earlier in collaboration with these great physicists, and let me actually move that away. And the other one is, well, it's going to be out soon in collaboration with Tracy Slack here at MIT and Yuri Smirnov at the Stockholm University. So I'm going to, okay. I'm going to start with a brief introduction, just set the stage and ask the main questions I want to ask. And then I'm going to talk about two different models, a confining dark sector model and just a very next to minimal generalized freeze-out model. I should say these are two disjoint talks. So I decided to kind of put them together and make one talk out of it because of the reasons you will see. But because of that, I'm gonna sweep a lot of details under the rug, especially in the first round. So if you have any questions, please ask. There's gonna be a lot of details that I'm not gonna cover, okay? Feel free to ask any questions you may have. So okay, let's just start. As I said, I'm gonna talk about dark matter. We know dark matter exists. We have evidence for its existence. And different observational evidence we have, they all point toward a consistent picture in which around a quarter of our universe is made of this unknown particle. Now, the fact that dark matter abundance and standard abundance are this close to each other, only order of one number different, has motivated a lot of people to think maybe there is a portal between them. You might think, wait, there is a factor of 5 difference, but a priori, there is no reason for these two abundances not to be orders of magnitude apart from each other. Now, a lot of the models that people have considered in that context are minimal thermal models. And what I mean by that, it's essentially captured in this famous picture that I'm pretty sure all of you have seen hundreds of times. I'm showing the abundance of dark matter particle. Right, we're adjusting that good. I'm showing the abundance of dark matter particle here as a function of its mass over temperature. And for a heavy relic, its equilibrium abundance goes down exponentially. And when we have this portal, it keeps the abundance in thermal contact with the standard model, but that after a point, it just cannot keep up because the particles are becoming so diffused and rare. So the abundance freezes out. And the larger the interaction cross-section, the longer we stay in equilibrium and the smaller the final dark matter abundance will be. This is the usual thermal dark matter picture and freeze out. Now, that thermal dark matter picture, which I'm showing in this plot here with that WIMP rectangle, WIMP is standing for weakly interacting massive particle, have a natural mass range, roughly in the GeV to 100 TeV mass range. And in that plot, I'm showing the dark matter mass versus an interaction rate with the standard model, and I'm showing different proposals that exist out there. And the thermal ones that I was telling you are living there in that small part. That upper bound on dark matter mass, 100 TeV, that is called the unitarity bound. And the reason is that if we want to get the right dark matter abundance through these thermal scenarios, we need to have a particular cross-section. And if we go to masses higher than this, the cross-section, even the unitarity bound of the cross-section, which is the maximum cross-section we can have, is just too small. And a small cross-section means we overproduce dark matter. So naively, without doing anything extra, beyond this bound for larger dark matter masses, we just produce too much dark matter through simple freeze-out mechanism. And that's what people call this bound unitarity bound. Now, these models, these thermal guys, are not the only option for dark matter out there. As you're seeing in this parameter space, and this is not a complete parameter space either, there are many different options, like axions are out there. There are many different things that are in a completely different part of parameter space compared to the WIMP or thermal relics. Now, this, I think, should motivate you to think about mapping all possible dynamics that can exist in a dark sector. I mean, there is a very simple theoretical appeal to it. There is a particle out there. We know it exists, but we don't know anything about its dynamic. It's good to just write down and think about what kind of dynamics can exist there. But it also has an appeal from an experimental point of view. It's that once we tell our experimentalist friends, look at this part of the parameter space, or don't look at that part of the parameter space, we're giving them well-defined targets to optimize their experiments for. So if I somehow, for instance, in this parameter space, I could tell my experimental friend, you don't need to come up with any new experiment that can probe this part of parameter space. Nothing is there. Nothing interesting will happen there. But a lot of efforts, for instance, will be dedicated to this part and this part because we have well-motivated models there. Now, following this train of thought, in this talk, I want to study two very simple thermal dark sector dynamics. And I want to show that these two simple dynamics that I'm going to elaborate on are going to open new parameter space in new regions of the parameter space here. In particular, maybe I should show it for people on Zoom. In particular, in this part of the parameter space that naively we don't see anything, I'm going to show that with just very simple things that we add to the dynamics of the sector, we open up a vast parameter space here. Okay, and I have essentially two proposals for that. Before I go into the details of each of them, let me actually summarize them. One of them is a very simple freeze-out scenario where instead of a 2 dark matter particle going to 0 dark matter particles, what we usually call 2-to-2 interactions, I think about a general P2Q freeze-out, initial number of dark matter particles, how many of them go to some other number of final dark matter particles. And I also introduce an unstable relic that decays to a standard model and dumps entropy. And that entropy dump, we will see, is going to change the story a lot. And just to give you a taste, this is going to be one of the money plots that I will show you. Here I'm showing the mass of the dark matter particle versus the unstable guy. And I'm saying the dark matter mass can be in very, very high masses, and we still can get the right relic abundance if the heavy guy has a large enough lifetime. That's one direction that I'm going to elaborate on. The other direction
so
is,
just to be sure I'm following, the chi is the dark matter.
In this scenario, yes.
Some sort of
it's the unstable guy that decays to a standard model. And in the other scenario that I'm going to start with that, I consider confining dark sector with only heavy quarks, heavy compared to the dark QCD scale. Oh, sorry. And I will point out a very interesting and dramatic effect that happens during the confinement phase transition in these setups. And the upshot of that is that it modifies the freeze-out picture in this way. Here again, I'm showing the dark matter mass over temperature and its abundance. The dark baryons go through the usual freeze-out. And then at some point, at the point of phase transition, something happens, and I'm going to spend the rest of the talk elaborating on that, that the abundance just jumps down by a lot. And these two scenarios, by diluting the amount of dark matter we have, open new parameter space and will allow us, in particular, to go beyond the unitarity bound on dark matter mass, okay? So that was the executive summary, just a big picture. I will spend the rest of, I should also say that I'm just gonna point out the mechanisms. I'm not gonna point out a specific portal and work out all the signals, although I will show some plots about one model, but a lot of the details are left for future works, or well, the works that are in progress right now. I just want to give you the big picture of the mechanism. Okay, so that's the big picture, and I'm gonna start with the first model, the confining dark sector, and what we call dark matter squeezeout, unless there is any question. No? Picture clear? Good. So, okay, let's start the first model. We have a lot of different motivations to think about the confining dark sector model. I mean, take the fact that the standard model has a confining sector, and a lot of interesting stuff in the standard model happened there. Why not the dark sector? or the fact that a lot of different relics in the confining dark sector can become a stable and good candidate for dark matter particle, and so on. And because of that, a lot of people in the literature have thought about confining dark sectors in different corners of parameter space and build up different models with either meson or baryon, dark baryon, dark matter, or blue balls, or something called blue quark, you name it. But something that was missing from all of these, almost all of these studies, and definitely never worked out in the detail that we are thinking about it here, is the effect of the confinement phase transition itself. The question I want to ask in this section of the talk is, can the phase transition itself affect the dark matter abundance in such a sector? Okay, and I'm going to answer that in the context of this kind of models. Consider a simple SU tree, one flavor of heavy quarks, and conserve baryon number. This is like one of the simplest things you can do beyond the minimal dark matter models. So I will consider heavy enough quarks that we will have a first order phase transition. You probably have seen such a diagram in many lattice papers. Here, as a function of up and down quark mass and strange quark mass.
Just to be sure we can follow. A single quark which is heavy,
Yes.
or a lot of light quarks and one that's heavy?
No, only one
And
heavy
it's
quark.
heavy, okay.
And I'm actually going to repeat that again here.
Instead of the decuplat, there would be just the,
Just again, sir.
never mind.
Okay. So here I'm showing what the order of QCD phase transition would be if we had different up and down versus strange quark. If we go to this line, where up and down are heavy and decoupled, we have a theory with one flavor of quark. And if we go to heavy enough masses for that quark, lattice study has told us that the phase transition is going to be first order. Okay, so this area here is where I'm going to focus on and where my models are going to be living. Okay.
By the way, the fact that it's one flavor does not necessarily seem, for instance, you cannot use the skill model to describe this system because there is only one flavor. There is no abelian skill model. There was recently a model by
I mean, for the things
about NF equal to 1, but it's not easier.
For the talks, for the stuff I'm going to talk about, one flavor actually simplifies the picture a lot. But I can add 2 or more flavors of heavy quarks as long as they're heavy. And the picture changes a little bit, but the gist of it does not change. Okay.
But basically, you're interested in baryons.
Say again?
Because they're stable, that in the dark sector, and so they would be like the omega minus or the
right.
delta
You will
plus
get
plus or so on.
right. If you, that's why I said the gist of it won't change, but some details change, because if your flavor symmetry, as you were saying, is actually conserved, but instead of baryons, yes, we will have mesons as well. But again, some of this stuff, the separation I'm talking about, it still will happen there. So-
There's only unstable.
Yeah, sure.
By heavy, you mean heavy compared to the confinement phase transition?
Dark confinement.
But not far above, because then you have pure gate.
Actually, true. So the range I'm going to look at is the heavy quark, a factor of 100 to 10,000 heavier than lambda, dark lambda. Okay.
Okay, but right now, it's not apparent why you care about that very much.
So right
Maybe you'll
now,
tell us later, maybe.
right now, the only reason I care about that is that I want the first order phase transition. That's the main thing that gives rise to this effect.
First order phase transition in the dark QCD.
That's right. Yeah.
So I just a very light question. So if you consider all the light particles also.
Okay. Keep that questions for 7 slides.
Okay.
We'll come back to that.
Okay, thank
Just ask it if I forget. Okay, now let's look at the dynamics of the phase transition. Anyone, and many people in the audience have done this, have thought about these phase transitions, knows how complicated these are. And these are not really well understood, and I'm not going to claim we are expert in understanding how the phase transition goes through. We just take some known lattice results and some simple equations from Kolb and Turner to look at how the phase transition goes through, what the bubble nucleation rate and all of things like that, and come up with an approximation. which is good enough for the purpose of our calculation, okay? But there's definitely improvement that can be done there. With that in mind, let me talk about the phase transition. So here I'm showing a plot of the fractional supercooling in the universe, T minus TC, TC being the dark QCD or dark lambda, and as a function of time in units of Hubble type, okay? So this is what we are saying our result gives us as for what happens during the phase transition. There are clearly 3 distinct regions for the amount of supercooling during the phase transition. Let's explain what happens during each of them. So first, before the phase transition, universe starts in the deconfined phase, and the order parameter we should keep track of is the free energy. The free energy is lower in the deconfined phase compared to the confined phase. At T equal TC, they become equal to each other. That's the definition of TC. And after that, when we get a little bit of supercooling, the confined phase becomes the preferred phase. But they're almost degenerate for a while, and there is a barrier between them. That's what lattice tells us. That's why we have first order phase transition. The tunneling rate between them is initially very low, so nothing happens. And we keep supercooling, and the confined phase becomes more and more preferred. At some point, when we get to that point, extensive bubble nucleation happens because the energy difference is large enough that the tunneling starts happening all over the universe, and bubbles of the confined phase nucleate everywhere and they start growing. Now, these bubbles, their emergence and their growth is accompanied by heat release, because this is a first order phase transition. We have a latent heat. When we convert the deconfined phase to confined phase, energy is released.
You're saying that, and we know enough from that as PCD to know what the shape of the potential is and calculate this 0.0008 number.
Yeah.
Or is that just meant to be a sort of
So there is one point, there is one parameter, and that actually gets into the V, that we actually put in from some approximation. Other than that, everything else we need for this behavior comes from lattice. Lattice results tells us what the latent heat is, tells us what the tension of the bubble walls are for this phase transition. They have been studied. I mean, the name you want to look for is Andreas Karsh or Ben Svititsky. They have done a lot of these things. So that heat release can heat up the universe, okay? And the heat release here, the latent heat is large enough that it can actually heat us back right very close to T equal lambda or T equal TC. Now, when that happens, if the bubble's growth, which is exponential here essentially, keeps with the same rate, we just release too much heat and the vicinity of the wall becomes very hot. It becomes even hotter than TC, at which point the confined phase bubble is not the preferred phase. Okay, there will be a pushback against it. So we need to get rid of that heat, and that get rid of will be done through diffusion. That heat should actually diffuse away so that the bubble can grow. So this essentially tells me that from that point on, the growth of the bubble is clipped by the ability of the plasma to diffuse away heat. And from that point on, the velocity actually changes. Instead of 1, it becomes something a little smaller, and the bubbles grow with that velocity. Okay? Good.
And I'm so slow keeping it up with you. So do you really care if it's SU3 as in the gauge group, or before you're talking about flavors, but
can you also keep that question 6 slides? I hope I'm not saying the number wrong. We'll come back to your questions. Okay. Now, this was all before the percolation. Bubbles nucleate, they grow, but they are initially isolated. Eventually, they grow and they make up order 1 fraction of the universe. They run into other bubbles. They realize there are other confined bubbles out there. They start coalescing. And this is the percolation time. They merge with each other. And they merge and become larger bubbles. Interestingly, you can argue that the time scale for these mergers becomes longer as you go to larger bubbles. And the reason is very intuitive. I mean, when 2 bubbles merge with each other, they have to move around. If they're larger, they have to move around more matter. And it just they have the same surface tension, it just takes time to push more matter aside. So keeping that in mind, kind of like the freeze-out logic, gives you, at some point, you find that the time scale for a bubble merger becomes longer than the whole phase transition time scale. And that tells you essentially the size of your bubbles are clipped at that point. That gives you a typical size of bubbles for after the percolation. And we get this thing from that simple analytic estimate I told you. We get this for the size of bubbles, and you can actually even numerically check it in our code and see that this is actually a pretty good approximation for the size of bubbles. However, again, these are very complicated stuffs. This is our estimation, and actually this is the main source of error in our calculation in that slide 17 that I'm gonna talk about. This is the main thing that gives rise to uncertainty. But at least it provides us with some approximation of what the size of bubbles are, and they're going to be relevant for our calculation. Now, this was all about the phase transition itself. What's happening to the quarks during all of this? Where are they? The quarks are heavy enough, a factor of 100 or more, that they decouple, they freeze out before we reach the phase transition temperature. And since they are actually very heavy, the gauge coupling is essentially perturbative, almost perturbative, and we can use the usual techniques we have to calculate the freeze-out abundance before the phase transition. Once we do that, you can check and find that by the time we reach the phase transition, the abundance of the quarks is very diffuse, and they are essentially a factor of orders of magnitude larger than 1/λ separated from each other, lambda being the dark QCD scale. Now, you may ask, wait a minute, colored particle more separated than 1/λ, that does not make sense. No, it makes sense. We're talking about deconfined phase. Lattice studies again have shown us that in the deconfined phase, the two sources of colors are well separated from each other, even a factor of a few times 1/λ. They don't see each other at all. The potential between them just completely becomes flat. Okay, so there is no paradox there. And from the point of view of each,
I'm confused. So we're imagining, we forget regular particles.
Sure.
So you have one flavor of a fundamental of SUN, and then it's going to turn out to be 3 maybe.
Right.
And then we have gauge bosons. And so
That's
we have
right.
lots of QQ bars and gluons.
right?
And now you're saying that the transition occurs when there's a lot of gluons but no QQ bars.
I'm not saying no
But
QQ
almost
bars.
not.
Yeah, the abundance is much
And you're
smaller.
talking
Than,
about, so this is not a chiral phase transition, this is. the
no,
confinement.
it's not. No, it's not.
But
Also,
oh, I see, and because they're very heavy, they freeze out relative to gluons, which are light. Okay.
yes, much earlier. Okay, you didn't. I was waiting for you to ask about that as well. Okay, so from the point of view of each quarks, they're alone in a vast deconfined universe before the phase transition. Okay, now the phase transition happens, bubbles nucleate, they grow, they run into each other, percolation happens. Let's see what do they do to the quarks. Consider an incoming quark coming into the wall of the confined phase, and it's still in the deconfined phase. It has a much lower energy when it's in the deconfined phase, because it's deconfined phase, gluons have the bimass, it's a screen. But if it goes inside the confined phase, it's an isolated source of color in the vast confined phase. It has a huge energy. So the quarks essentially see almost an infinite energy barrier in front of them. So what happens is that when a quark runs into the wall of the confined phase, it deforms the wall, it pushes it in, but the wall doesn't let it go inside the confined phase. It just acts against it and it exerts some force, it has a surface tension. At some point, it brings the quark to a halt and like a slingshot shoots it back into the deconfined phase. So the quarks are essentially trapped in the deconfined phase as long as they're isolated.
My ask, yeah, because it's related to last sentence. So what is the fraction of these quarks? Like single quarks, and what? Because some of them form bound QQ bar states. There's no confinement, but there's still some Coulomb attraction. Right? So,
Absolutely, yeah.
and I would think that
I will show a plot of how many of them we have compared to these guys.
right.
It's like even 10 orders of magnitude suppressed, more than that suppressed. So we don't have that many of QQ bars compared, or QQQs compared to free quarks in the deconfined phase.
Yeah, like
And then you have-
neutronium, right?
Yeah, I mean, if you have an approximate, since it's actually we're in the limit that they are heavy, the
Right.
bounded state is the same, almost like we live on the Coulomb branch of the corner potential. We can calculate the binding energy and everything.
Right.
So we can use that, and we find that for these masses, we don't have that many of those guys.
I don't understand the picture. You have these bubbles at the end of the phase transition, but they occupy all the space, or basically.
Let me clarify the picture a little bit better.
So sorry, well, why does the incoming part feel infinite large?
Why does it feel infinite?
Yeah.
Again, because
Sorry, yeah, looks like-
the two energy, consider these two cases. So a single source of color inside confined phase.
Yeah.
You know, it has essentially infinite energy, but outside there, it doesn't have any energy. It's essentially because the gluons have a Debye mass.
Yeah.
Okay, so that energy difference means just
Oh.
energy barrier.
Oh, okay.
But actually, I guess the way you would maybe more accurately want to phrase it is that the lower confined phase simply won't emerge containing a quark because it would cost too much
Right,
energy.
yes,
So that
yes.
suppresses nucleation of the bubbles.
That's right. Yeah, that's another sake. Yeah.
Anti-nucleation of the bubbles.
But usually we don't consider single quarks in this in the in the presence of this confining. We should talk about hydrogen. We should talk about the fluid that is interacting with
Right.
the phase of this confining.
Right, right. It's just that I'm saying that as long as let me see, how do I want to say it differently? Okay. Those two pictures, both of them work. It's just as I want to see what happens to one single quark, and the fact that it doesn't go in as long as it doesn't find anyone else. I mean, that's the part that is going to be relevant. Sorry, I didn't give you any useful bit of information there. Let me review the picture for you. So we start slightly below the phase transition temperature. Most of the universe is in the deconfined phase, the lighter purple shade, and bubbles of the new phase, confined phase, nucleate everywhere. Okay, and the quarks, the dotted guys there, sorry, are oh, that's even worse. The quarks are diffused across the deconfined phase. Now, phase transition proceeds, the bubbles grow, and they take more of the space. They also push the quarks aside, exactly because of what we were talking about. They don't let any quark go inside of them as long as they're alone. And the quarks are very diffused right now. At some point, they make up order one fraction of the universe. They run into each other, they percolate, and the table is turned. It's like the Witten's cosmic separation of phase paper. We will end up with most of the universe in the confined phase and a small isolated pockets of the deconfined phase. Okay, and the quarks are still trapped in there. Now, let's look at one of these guys. Again, once these guys form, initially we have checked and the quarks are far apart from each other. As time proceeds and phase transition moves forward, the pocket contracts. As it contracts, it brings the quarks closer to each other and into interaction with each other. Okay. Now, some of the quarks annihilate. And QQ bar goes to gluon, and we assume there is an unspecified portal to a standard model here, and the glue balls go to a standard model. But some of them can form stable color neutral bound state, like baryon is the QQQ baryon is the simplest of that.
I don't understand this picture yet. So in this of these blue regions, you imagine there is just single quark or anti-quark?
No. Blue regions are
No,
the
white region. Is in these white pockets.
right.
Are you imagine single quark?
No. A lot of them.
A lot of
Orders of
them.
10 to 20, something like that.
Right. Okay. But because they have to be color neutral, otherwise it will be.
Yeah,
strange
that's something that is, yes, there. Okay, what Sergey is saying is that assume you have 8 or 10 quarks in there and 10 there,
Right.
then the whole thing, think about Gauss law around it, the whole thing has a net charge. So there should be some string between them. I'm assuming such a thing does not exist. I don't have a good answer why everything should be color neutral.
But the picture is that each of these pockets is color neutral, right?
Yes.
Right, because otherwise it would carry
Right.
too much energy, so it simply
Right.
can't create the bubble.
Yeah, and they move around like crazy. I have no idea what
That
happens.
seems
there.
like the least of your problems.
And so then you expect
Thinking that
there will be lots of mesons now instead.
Inside, okay, good. That's what we wanna do. We have a bunch of particles in there. They're being smooshed together. We can solve a bunch of Boltzmann equation
Right.
to find how many mesons, baryons, and all of that we have in there. Okay, and the thing is that once we form color neutral particle, these orange dots, they're not bounded to the pocket anymore. They don't feel that energy barrier. They can go out. Okay, so what we want to calculate is when the pocket shrinks and squeezes out completely and vanishes, what fraction of the initial quarks in there survive in the form of stable color neutral baryons. Okay, and we call that the survival factor S.
So basically, this orange things is a mixture of mesons and baryons, and you want to find out how many baryons are there. because-
Yes, but here's the thing. Mesons are extremely short-lived. I have one flavor, and here's one place that the flavor thing comes in. I have only one flavor, QQ bar, decays to blue balls, and I assume an unspecified portal to a standard model. Blue balls decays to a standard model. Okay, nothing protects it. So the only thing that survives until today is the barrier.
So you're assuming that decay rate for blue balls is fast enough to standard model then.
Okay, that's part of the follow-up model that we are writing. If the glue balls are actually long-lived, they don't change the picture here much. You can include it in the Boltzmann equation, but nothing, the result doesn't change. But they can actually dump entropy later on and change the story a lot. But for now, let's assume glue balls are decaying very fast. They're not relevant for this picture. More
So the
questions?
fact that it's dark is only because there is one single flavor. That's the difference from.
No, that's a different thing.
The only difference.
Sorry, you said the fact that it's dark is because.
Well, I mean, suppose that you raise the word dark and you describe to us the evolution of the real world, the real matter, standard model. What would have been different apart from the fact that it's one single flavor?
Well, we don't have a first order phase transition in QCD. So none of these things will happen in our QCD.
Because we have more than one flavor.
It's not just that, it's just we have more than one flavor and they have a combination of masses that at least lattice tells us the phase transition, the standard model QCD doesn't have a phase transition, essentially it's a crossover. So in the plots that I showed you earlier, in this plot, the standard model lives somewhere around here. Okay, but I'm talking about a model that will take us there. Oh shit, I'm going the wrong way. So okay, I gave away punchline. As I told Sergey, we have to write down a bunch of Boltzmann equations and solve them. There is something like 20 different interactions that we have to write down and solve, and a bunch of different relics that we should keep track of. I'm not gonna bore you with that. One of the details that you can ask me.
Why is it complicated? I don't understand.
You have to
It's just,
calculate.
Three particles.
Yeah, but
The
okay,
baryons
think
and
about
antibaryons
this.
are identical.
Okay. If I tell you, write down the Boltzmann equation for me, you have to tell me all the interactions that happen between a baryon and a diquark and a quark and a diquark and a quark and a baryon, all of that. And you need to know the cross sections between all of them.
Except that you're saying they're all in the unconfined phase, so there are no diquarks.
There are diquarks. There definitely are diquarks in the.
Not in the low temperature.
They are. That's what Sergey was asking as well. You will have bound states even in the deconfined phase. It's just that you the number is very
Sure.
low. And you have to, as you compress the whole thing, you have to calculate what fraction of them quarks go into baryon. So what you do is say one quark and one quark interact and give me, well, okay, in this notation, that means one quark go to a diquark and a blue one. And then that runs into another quark, gives me another thing. You have to keep track of all these interactions.
So the dynamics, all of this happens within one Hubble time?
Yes, even 0.1 Hubble time, 0.01 Hubble time, sorry.
0.01. Yeah, also the phase transition, but I wonder what sets that number? Like what sets this 10 to the minus 2 Hubble times?
Right,
Does
I
that
mean,
depend on the mass of the quark?
it depends on the nucleation rate of the bubbles, and we dipped in that plot that I was showing, and also the velocity of the growth rate of these bubbles.
Right, but my question is, so how does the mass of the quark enter?
Oh, the mass of the quark essentially does not enter this. So the phase transition and the code we also wrote down and solve all of this for the phase transition, it's essentially pure Yang-Mills.
Okay.
The quarks are very diffuse.
Number of colors is the only discrete.
That's
free parameter.
right, and that only is relevant to tell you if you have a first order phase transition or not.
So just so we're oriented in what's going on in the visible sector, what temperature would this be happening at in our sector?
Again, that is slide 17. Sorry. Wow, that's slide 17, better delivered.
But just roughly, just the answer.
But I'm going to talk about phase transitions around TeV to 100 TeV. Okay, we want to solve Boltzmann equations. And for one mass point in our parameter space, I do that, I solve it, and I can find the evolution of different relics in the pocket. Here I'm showing as a function of the pocket radius, this is not bubble pocket, sorry, the fractional abundance of different relics. Like the red line is free quarks, the green one is a diquark bound state, and the brown is a stable baryon bound states. And you see that initially, the time goes from left to right. You see that initially, we don't have that much diquark or baryons in the pocket. Most of them are free quarks, and as time passes and they're compressed and brought together, the abundance starts building up because quarks run into each other, make them, and at some point when you compress them more, those bound states even annihilate and their number goes down. But you can show, and I'm not going to go into that, that the survival rate is given by something like this. Initial number of quark normalized to, well, integral of the baryons that run away. That's the definition. But that integral simplifies to something like this. And this guy here is the number of baryons in the pocket. So the survival factor is essentially an integral of this black curve. So once we solve the Boltzmann equation for any point in our parameter space, and we take this integral, we find the survival factor, okay? So let's look at different points in the parameter space and see what survival factor we get. There it is. My parameter space, I'm talking about lambda from 0.1 to 1,000 TeV. And I was right, it is a slide 17. And from 100 to 10 to 4 ratio of m quark over lambda, okay, very heavy dark quarks. And in green lines, I'm showing contours of constant survival factor. And that was the shocking part to me when we first actually did this calculation, that we get orders of magnitude suppression in the abundance of dark matter across this space. Just to also orient you more, remember I was telling you there is this, those contours are contours of constant dark matter mass, dark baryon mass. That guy is 100 TeV dark matter mass. That's the unitarity bound on thermal dark matter relics that I was telling you. And I'm actually focusing on the parameter space where almost all the dark matter masses I'm looking at are heavier than that. And I'm going to claim that with this setup, we get the right relic abundance over this line in the parameter space. And the reason we managed to go beyond that unitarity bound is that we have this gigantic suppression in dark matter abundance. Okay. Now, I mean, the
suppression basically comes from just because most of the quarks just annihilate in these bubbles. QQ bar
right.
go to blue balls and
goes to a standard model. Yes. Right. Yeah. Now, we have to talk about uncertainty. And as I told you, the main source of uncertainty is like that the size of the bubbles. I'm not going to explain why that is. but we don't really have a good way, like how in LHC we parameterize uncertainty. We don't have a good way of parameterizing that. Just to capture the effect of that size, we vary the radius of the pockets by Fudge factor of 0.1 to 10 and see how much it actually moves our dark matter, our relic abundance line. And we see that it moves within that light shaded region. Okay. Unfortunately, I can't tell you a very sharp and narrow line, but also this is a super complicated problem. I mean, I'm pretty sure even right now I'm somehow underestimating my uncertainty.
So may I ask you just for curiosity, if there were no this complicated story with first order phase transition, it was crossover or smooth phase transition, still you would think you would lose lots of quarks because they would go into mesons. So
Right.
that's a question.
So
What
that
fraction of
work-
quark goes to baryons versus what fraction?
That work has been done by one of our collaborators, Yuri
Right.
Smirnov, and his collaborators in 2017.
Mhm.
And they were essentially arguing it's because of combinatorics. It's like the probability of a quark running into a quark or anti-quark in its next interaction. The suppression you get is an order 1 number, 0.1, for instance.
Okay, you think there should be also some Boltzmann suppression, no? Because baryons are heavier.
The baryons I mean, not compared to QQ bar, are they?
Other three has.
Yeah, because
It's a heavy quark limit.
but for heavy quark limit, and especially if it's not SU3 but SUN, then
Oh
okay,
yeah, in that
then,
case, yeah.
then
the
you can get very large separation.
But
because it should be
okay,
much-
let's say it like this. The suppression will be like 1/n, essentially, something like that. Here I'm talking about no, it's actually orders of magnitude
Well,
lower.
they're also one could get exponent, right? Because Boltzmann suppression.
So I definitely have to. Okay, let me actually go back and look at their paper. We can talk about it right after the talk.
Okay.
We can go through the paper together. But in this setup, the upshot is that we can actually get the right dark matter abundance in this mass window, orders of magnitude beyond the unitarity bound. Now let me answer the question you had. What if there was one question about number of colors? What happens is that instead of a three quark, if I go to SU4, the stable guy is a 4 quark bound state. So the line that will have another line for another bound state. And I get even further suppression if I go to larger gauge groups. I'm trying to remember your question. I forgot it.
Yeah, my question is why don't we just use the light quark?
Right. If you get the light quarks, when the light quark runs into the wall, it pushes into it. But then it's actually not that costful for 2 quarks, quark anti-quarks, to emerge from vacuum. Okay, that's the Schwinger mechanism essentially. Since quarks are light, the rate for that mechanism is not suppressed. So you won't get this kind of suppression. The quarks are essentially not trapped in the pockets.
Oh, so
And
it
there
just
are-
goes through it.
Yeah, they go through it. There was another work by Filippo Sala and collaborators a few months before our work that looked at that limit. They still argue that there is some suppression because of some showering effect like at LHC. I don't remember it exactly, but again, Filippo Sala, early 2020, look for one of his paper on that. But we relied on these quarks being heavy so that the string breaking is completely shut off. Okay. Now,
Sorry, but even the quark is light, it can form the stringer pair. Well, you can still have like 1 quark left in the deconfining phase.
yes,
like-
yes,
like
you
the-
have it. But I'm saying even if all of these things happen for light guys and they get squeezed out and their abundance goes down, they still have left some stuffs in the confined phase. When they ran into the wall, they left something that goes on. And that's like order 1 fraction of initial quark survives. So, I mean, 10 to minus 6 times the original number is negligible.
But the number of quark left in the deconfining phase is also determined by the accidental asymmetry, right? Even for light quark, if the baryon symmetry is not broken.
We're talking about dark sector. I didn't say anything about asymmetry in the dark sector. I think you're talking about asymmetry in the standard model.
No, the baryon asymmetry, the accidental asymmetry for each pocket.
Okay, so you have read our paper. Yes. So one thing I didn't, and hold on. Okay, I definitely won't have time to talk about the other half of the talk, so I'm just gonna go into more details in this half. One thing I didn't tell you guys is that when these bubbles form, let's even assume that we have net zero color in here, but it's not guaranteed that I will have zero baryon, dark baryon asymmetry in the pockets here. I mean, it's a Gaussian random number, and sometimes the average is zero, but I will have an accidental net non-zero baryon number in here. Okay, and since baryon number is conserved, that actually puts a lower bound on our survival factor in these bubbles, in these processes. Okay.
Sorry, isn't that mean that also there is non-zero?
Right. So does it also apply to the light quark?
Three quarks in this bubble, but three anti-quarks in this bubble.
But that means each of the.
Each of the quark can be
color
zero.
Yeah, okay, yeah.
So, and about your question, yes, that can also happen for baryons, for light quarks, if you can get them to this point. But what I'm telling you is that that picture at that stage, when a quark runs into the bubble, I hope you see my cursor actually. In this picture, when a quark runs into the bubble, it does not get pushed back essentially. Well, yeah, one quark gets pushed back,
right. I agree with it.
Goes in. Okay, so all of these things I'm telling you is irrelevant for the case of light quarks.
Yeah, but for light quark, will it attach on the wall? If it's not penetrate, but not push back. But
follows again.
So okay, so if I have a light quark when it's approaching to the wall, to the domain wall, and it can be there may be a meson go through the wall instead of the quark of the light quark, but will the light quark still attached on the domain wall if it's not bounce back?
I'm saying I don't know. I'm saying whatever happens to it, it's not actually affect the calculation of the abundance in that case. So
okay.
we can actually go into more details on that if you want that.
I see, okay.
Let me see. Okay, actually, yeah, I think I'm gonna wrap this part up and very quickly mention the other part. So the upshot is that this squeeze-out mechanism can suppress dark matter abundance, open new parameter space, and of course, we're talking about very heavy dark matter particles, so maybe we need new search strategies. The searches that we have, like for instance, collider physics searches, there is no hope that these things can actually be detected in our collider searches. Maybe it's useful to think about new ways that we can probe these kind of models, and don't ask me why, we can talk about it after the talks. I would say gravitational waves are the best way for these things. And a specific model for this thing is something that we're working on right now. I didn't tell you about any portal between these guys and a standard model. I just said the portal should exist because we want to dump the global's abundance into a standard model. We are now introducing that portal in a simple model, and we're looking for the signals that you can get from this model in various experiments. The signals most of them are very suppressed, as I was telling you, because we have a very heavy dark matter.
It probably can be dumped to some dark radiation, right? There's nothing forces you to dump it to the standard model.
Yeah, sure, true. Yeah, that again, you can think of a model like that, of course. But yeah, look out for another paper with Tracy and Yuri being out in the next, I don't know, 1 or 2 months. So, okay, with that, I absolutely do not have time unless I can go over time.
Can I ask a question on the previous one?
Sure.
Maybe you just mentioned this and I missed it. As you're going through the space transition, you mentioned that the domain walls, like, they're really hot. Are the quarks in the deconfined phase also heating up then as a result of the collisions with this domain wall?
Not much. Everything, the kinetic equilibrium is maintained everywhere. Again, that unspecified portal. Actually, you don't even need that. So dark quarks with the dark blue ones, they are talking to each other, they're exchanging energy. The number changing process is suppressed, but the process that can keep them in kinetic equilibrium is still there. And then the blue balls, we're assuming has some portal to a standard model that keeps it in kinetic equilibrium. So temperature is essentially uniform everywhere. So, okay, I don't have time to talk about this model, but let me just very quickly give an idea of what the what we're gonna do. Well, what the point of this section of the talk is. Usually we talk about, when we talk about freeze out, we usually say there is a 2-to-0 interaction or a 3-to-2 interaction that gives rise to freeze out. And depending on that type of interaction, for instance, for WIMP, we have 2 dark matter going to 0 dark matter, hence the notation. It's different from the usual notation. Depending on the type of interaction, we usually hear that there is a preferred mass window for the thermal dark matter particles. And also for interactions with higher number of initial particles, we say the natural mass window for them is at lower masses. So we usually do not really consider them because there are a lot of bounds on them. What we just point out is that if you consider entropy dump, actually, yeah, let me just say it in words. If you consider entropy dump, and that is something that people have studied before, Asher has a bunch of papers on it. If you consider that effect, you can actually move around that window of mass for any type of dark matter freeze out interactions. And in particular, we just wanted to point out that even if I consider a freeze out with 3-to-2 processes, like the SIMP processes, or a freeze out with even 4-to-3 processes, like we don't even have a name for that, we have a gigantic parameter space available. Here I'm showing the mass of the dark matter versus the mass of an unstable particle that decays to a standard model. And we change the lifetime of that unstable by as a free parameter. And as we vary that, we find that for every point in the white region, we can get the right dark matter abundance. If we have the right lifetime for this guy. I'm essentially saying all of this for people who have worked on dark matter dynamics before. So I'm so sorry for I have to apologize to the rest of the audience because I don't have time to elaborate on these. But I just wanted to point out that that's the main point that I wanted to get across here, and that probing these heavy parts of the parameter space, actually the best way to do it is look for early matter dominant epochs. And there are ways to do this. I'm thinking about some ways. If you're interested, we should definitely chat about these things. I'm going to be around the next 2 days. But also a specific model, never mind, screw that. With that,
like you said, people have considered entropy dump. So the new thing is the application to SIMP.
The new thing is application to SIMP and higher order of interactions. Yes. Also, Asher definitely knows this better than I do. We also point out that for even lighter dark matter models, the entropy dump opens parameter space because your cross section can be smaller, so the indirect detection bounds and direct detection bounds will be suppressed, and we open parameter space there. And these are thermal models, not non-thermal ones like cannibal dark matter or things that Rusbeh already worked on. I don't know if you know off the top of your head if people have thought about entropy dump for light dark matter.
Off the top of my head.
Okay, so that's also maybe something interesting. So let me summarize the talk, and essentially I'm just going to summarize the first model of the talk. I told you that it's really important to map out all possible dynamics that can happen in the dark sector. And in this talk, actually, I had time to only cover one interesting and previously overlooked effect in thermal dark matter models that opens up a vast parameter space. What was that dynamic? It was that consider a confining dark sector with one heavy flavor of quark and conserved baryon number. We showed that toward the end of the confinement phase transition, we have this dark matter squeeze out stage where dark matter is trapped inside isolated pockets of the deconfined phase. They're brought together and they efficiently annihilate away. And it gives rise to a gigantic jump in their abundance after they're frozen out and during the phase transition. And because of that, the right dark matter abundance in these setups without any further model building can be obtained for masses in the ballpark of 1 to 100 or 1,000 TeV, give or take uncertainties. I'm gonna stop here. And if you wanna hear more about the other part of the talk, we can chat about it afterward. Thanks a lot.
Questions for Pouya?
I have a comment. So in the past, there used to be also theories with the two confining the scale, and they refer to either technicolor or hypercolor.
Yes,
But there, the purpose was to create quarks as composite of
something else,
initial-
yes.
The difference is that in your case, the baryons of this other scale do not talk at all to the ordinary standard model.
Not direct, yes, not, let's see. Okay, no, I did not talk about the portal here. You can still introduce, say, a Z prime portal, but the kind of models you're talking about, they're essentially more I would call them more UV complete, like Technicolor models, for instance. And I actually never thought about Technicolor and dark matter, but people have thought about them in other contexts, like God or explaining the hierarchy problem. I'm pretty sure somehow you can embed this thing in Technicolor models somewhere, but I mean, we have a Higgs.
Well, but there, the main purpose was that you know, the baryons, the singlets of the hypercolor carried the color degrees of freedom, right? So there was an interaction between these baryons and the standard model, but for the dark matter purpose, you don't want it, right? So
Sure.
Okay, so that's the difference.
Can you say a little bit about the detection prospects? You said gravitational waves, but is there any hope for direct detection in the lab, or is it too heavy?
Actually, yes. Let me see if I have the plot for.
So gravitational waves, you mean just from the first order phase transition?
From the
right?
first
Because
order
it
phase
didn't have
transition.
this range, right?
Yeah. So, is it in here? Okay, I don't have a plot about it. Sorry, I don't want to show that to confuse you. For the gravitational wave, there is a subtlety though. At least in the model that we are using, initially the bubbles were moving fast. So we get a sound wave effects from there, and we can actually detect the gravitational waves from that part. But after that, we were claiming that the bubble balls move more slowly, like with 10 to minus 2 velocity, or even maybe lower than that. And for such non-relativistic velocities, there is no prospect of detecting. So all we care about is that initial explosive growth of the bubbles at the phase transition.
And that's more or less governed by the size of the bubble, be the inner quark distance.
Not the quark
Because
part.
the minute they get big enough to start trying to push these super heavy, right? You just showed us that the
Oh, okay,
mass
good,
was
good.
1,000 times bigger than lambda.
Right.
And so once it's trying to push those ahead of it to keep them out of
You're
the-
saying there is a quark pressure, and yes, the quark pressure will be relevant, but later on, when actually the pocket formation happens. Before
That's
that,
only, that gets to when the pocket radius is similar to the.
one over
quark.
lambda. Okay, yeah, I
So
see what you're saying.
the number density of the
Is
quarks.
large, yes. At that point, yeah, the velocity is very low, but the gravitational wave comes from way before that. And when the bubbles of the confined phase are growing, they do run into quarks, but the quarks are so diffuse that the pressure that they exert on these guys is essentially negligible, even though they're very massive. So they do not initially intervene with the growth of the bubbles. I know it's a little bit counterintuitive.
But I thought it's important to get gravitational waves. It's important to have percolation, right? Because single bubble doesn't produce.
Well,
there's no quadrupole, right?
So that's what okay, yes, that's what I thought as well. And I thought, okay, so we don't get any gravitational wave with these velocities. But a gravitational wave person pointed out to me that no, even the initial growth gives rise to some sound waves in the plasma, and they give rise to some gravitational wave that you might be able to detect.
In LIGO, this is what's the relevant frequency range?
So let's see, the frequency range should be relevant to lambda. 1 TeV is roughly the ballpark of LISA frequency, which is 10 to minus 4, 10 to minus 5 hertz. LIGO is in the hertz or 10 hertz regime. So if you want to see these things, gravitational waves, even if they're visible, it's going to be LISA, BBO, or DESIGO, these future experiments.
When the bubbles actually collide though,
Right.
then you have a non-spherical object and then they combine, if I think of a bubble collision, they combine into a single bubble.
Right.
Is that process not going to, as these things settle into would that not?
They're doing it
Actually,
slowly,
that's a
right?
good point.
But they're slow. I agree that the collision itself is slow, but then they
The merger is fast. so
merge
a
and that's
good point.
fast.
Mhm.
And that's definitely got all sorts of multiples.
Okay, I think it's actually worth thinking about. I have no idea how to do the calculation here. It's, I should write it. Oh, yeah.
Yeah, so you have one question about gravitational signal. So if assume in the future we really find something, these can we tell this because not only this model will have the bubble collision, but also electric phase transition also have bubble collision, which also have similar. But
So I think you're asking if we see something at
yeah,
least,
so
can we
we
say it's
tell-
from these
yes,
things
it's-
or other
it's
things?
from this model, or
I mean-
no, or because or do they have some?
Yeah, you need to know,
characteristics?
the spectrum in the gravitational wave. The
Yeah,
thing
yeah.
you get from these guys, for instance, the spectrum will be different than what you get from, say, cosmic strings gravitational waves. But any other phase transition with similar identities, not necessarily confined phase transition, will give you the same spectrum.
Yeah.
So I don't think it's that easy to just see the spectrum and say it's this guy.
But
Because
even
you
if it-
distilled, sorry.
Even if you didn't have quarks in this hidden sector.
Yeah, exactly. The phase transition exactly would go as
So
it
it seems
was.
like it's totally insensitive to whether this is a mechanism for dark.
Right,
matter.
it's just that for gravitational waves, we distill from phase transition, we distilled every details of the dynamic into 4 quantities. Velocities, beta, which is the time scale for the gravitational wave, latent heat, and the temperature. So a lot of different models can have very different dynamics, but these 4 quantities are the same. So,
Yeah.
and back to your question about direct detection, yes, direct detection experiments will be sensitive to part of these parameter space, but it's actually a very small part. It doesn't cover. If I look at this plot, okay, I don't want to say something wrong. I'll look up the plot for you, but we cover like 1/3 of this line, for instance. We don't cover most of it.
Through what coupling? How do you couple this to the standard?
Right, in the model, okay, one thing also, this detection prospect depends on the portal. The portal that we use in the model for this is a Z prime. And just Z prime to heavy quark to a standard model. And there are reasons we chose that, but with that portal, you can show that for light enough Z prime, you can cover maybe around 1/3 of that.
I mean, even though you choose different other portals, it's still similar.
Other portals, I mean, yeah, but you have to calculate the cross section. But yeah, the calculation is simple, and the result probably is comparable.
Okay, we can keep discussing, but let's thank Pouya again. People should-
This one, Josh, 5 o'clock works for you?
Yeah.
Maybe it's just a dipole. Okay.
I didn't understand, so you're interpolating.
No, so let's imagine I just take 2 bubbles that are really slow and I just touch them together. Then they have to block into a thing, right? So
Why do
they're
you
gonna-
have to block quickly?
Because they want to minimize the surface area.
Yeah.
Yeah, but they still have to displace quite a bit of plasma around it,
Plasma,
right? And the
yes.
quarks will be like, imagine 2 spheres, so it looks
Uh-huh.
like a dumbbell. To
Okay.
make the dumbbell into a sphere, I have to
Mhm.
displace a lot of quarks, and that, I mean, doesn't that
That does,
displacing the plasma and the quarks?
displacing the
doesn't
plasma does define a time scale. And one of our collaborators actually estimated that. I still think that actually happens very fast. Yes, actually, it should happen relatively fast compared to the Hubble time here, because we found that we can use this approximation of these 2 bubbles going to 1 bubble as something almost instantaneous.
You don't actually displace, you gain, you displace less mass with the 1 bubble, 2 bubble case, no?
No, I mean, he says you have a
Okay.
dumbbell and you want to turn it into a larger sphere. This deformation just moves the plasma around it, and it just takes a time.
Yeah, like he's saying like imagine the bubbles grow slowly, right? So let's say there's two small bubbles, they grow slowly with the bigger bubbles, and then eventually they touch and you get sort of a dumbbell type of situation, and then why would suddenly like the speed of the wall? I mean, the final state would be, let's say, one big bubble.
I mean, you're saying that you need
Why
to
would it
place
speed
there,
up?
but you're in the other direction. There's pressure and there's
Yeah, you can squeeze
Right.
there and
And I'm just saying, like energy tells. I mean, the final one bubble state is the lower
right.
energy state.
Yeah, but the speed, I don't
I
see
see
why
what
it
you're
would suddenly
saying, yeah.
speed up.
I see what you're saying. Yeah, I don't have a good sense of the time scale. Let me think about it.
The interest is gravitational waves. Or?
Yeah, it's just
Yeah.
gravitational wave, yeah. The dipole. Yeah, but that's the other question. Is this just a dipole?
When people talk about gravitational waves from first order phase transition, it's this, right? Versus different.
Well, one of them is this. Yes, it's the bubble collision part. There is also the sound wave part that comes from two sources, either initial growth or even after the collision, you will give rise to sound waves. And there is some turbulence effects that is more prolonged.
But also usually when people talk about the gravitational waves, they're assuming that these are like, these thin wall approximation.
Yeah.
Right.
Where you can, these things are expanding at something like the speed of light and.
Yeah, so here are the heavy quarks for
Here,
the wall
that's
dynamics.
That's different. So,
Yeah.
So the question is, what's the time scale for this?
Yes.
Uh,
Yeah. Sorry, I don't have a good answer. I should think about this. But let's actually see. So we have a force of order lambda.
Stop recording.
Okay, sure.
This is not on YouTube.